Good morning.
So at the beginning, I'll tell you that next week we will have a quiz. I'll send out some topics to be prepared for, but right now I can tell you that the topics will be related to limiting reagent, to percent yield, to molecular equations, ionic equations, net ionic equations, and concentrations. We didn't finish last time discussion about some topics, so I want you to continue today, so you will have understanding of the topics better. And again, as I said, I'll send out the email about the quiz.
Doctor, when you will send email?
You mean email?
Yeah, email about topics.
Yeah, so let me just finish today's class, and after the class, I'll send the email.
Okay.
Doctor, can I ask you something?
Yes.
I already contacted you on the email about the quiz, previous quiz. I wasn't be able to submission the quiz because I had a problem in the internet. And I already contacted to Christina. She told me to contact with you on the email, but you didn't respond.
Yeah, so about these kind of issues, please contact the office. So and let them contact to
You
me.
mean,
So
you mean the manager? You mean the manager?
yeah, contact the manager.
I already talked with the Christina, but she told me to contact with you. She
Okay,
gave me two
so
emails with you.
okay, so I let's do like this way. So contact her again, and she can send me an email, or you can send the email, official email, that they allow you to take the quiz again. So then send me an official email that you are allowed to take a quiz. Otherwise, I'll not allow you to take a quiz.
Okay, thank you, doctor.
Any other issues?
Doctor, can we please, when we end the first lecture, complete without any break?
So usually we don't have a break during our class.
Okay.
So once the Zoom is off, I'll just restart it again immediately. So it just takes some time to enter the Zoom. That's the break we have. I mean, technically, we need to just break the Zoom because it's not in my hands. So this is how the Zoom works in this situation. So. All right, so we stopped here. So we were discussing about limiting reagent. We wanted to find, so we wanted to discuss about the example of how to find the limiting reagent. And in this particular example, we have urea, which is prepared. So this is urea, which is prepared by reacting ammonia. So there's the ammonia here with carbon dioxide. This is carbon dioxide. So once we react with 2 moles of ammonia with 1 mole of carbon dioxide, we create 1 mole of urea. So it should be plus here. I'm sorry. So this must be plus. And 1 mole of water. This is the equation according which this reaction proceeds. Now we have conditions. So it says that in the process of creation of urea, we started with 849.2 grams of ammonia. And this amount was reacted with 1,223 grams of carbon dioxide. We need to find which of the 2 reactants is the limiting reagent. So I'll just remind you that the limiting is the reagent on which depends the reaction. So if the The one is consumed, so the limiting reagent is usually consumed first. And once we used it up, the reaction stops. So now we want to find out which of these two, ammonia or carbon dioxide, will be used up first, after which the reaction will stop. Now let's just see. So let's just answer the very first question, A. Then we'll talk about B and C. So what is the strategy here? So first of all, what we need to do is that we need to convert grams of ammonia, because it's given in grams, right? So this is how ammonia is given. So we are taking each of these to find out which one is the limiting. So first, let's deal with ammonia, right? So we need to convert grams of ammonia to moles of ammonia, and from moles of ammonia to moles of urea. So we want to find how many moles of urea will be produced together. So in case of particular amount of ammonia. Okay. So how to find the moles of ammonia if we know the grams of ammonia? Do you remember that?
By molar mass, doctor?
Yeah, so we need to find molar mass first for ammonia. So the molar mass for ammonia is 14 plus 3. So 14 is for nitrogen, 3 is for hydrogen. So overall, it's going to be 17 gram per mole. So then we need to just divide amount of ammonia in grams by molar mass of ammonia. Okay, so this is what is given here. So mass of ammonia is divided by molar mass of ammonia. So, and we found, so what's going to be the answer here? Can you just calculate what is this answer here?
Okay, doctor.
$49.9.
Okay, so 49.9. What is the unit here?
Mole.
Right, it's going to be moles. So we found that we have, if we take 849.2 grams of ammonia, we found that it corresponds to 49.9 moles of ammonia. Okay, so now we need to find how much urea is formed if we have 49.9 moles of ammonia. So how to find it? So we need to look at the equation. So it says that 2 moles of ammonia produces 1 mole of urea. So according to the equation, it's like 2 moles of ammonia produces 1 mole of urea, right? So this is moles of urea. But we have in reality, we have 49.9, right? So then we need to calculate that 49.9
Yes.
is going to be X moles, right? So we need just to divide 49.9 by 2, right? So this is what is written
equal,
here.
yes. Mole of
Yeah.
urea equal 24.93 mole.
Okay, so the X basically is
Equal
24.93 moles
mole of urea.
of urea. Yeah, so this is what is written here.
Yeah,
Okay,
but I
so-
calculate on my phone.
Yeah, that's okay. That's good. So now we know that we have particular amount of urea which can be produced if we take a given amount of ammonia. Now let's look what's gonna happen if we take this amount of carbon dioxide, how much urea we can produce. So the strategy is the same. So we have grams of carbon dioxide, which is converted to moles of carbon dioxide, and then the moles of carbon dioxide is converted to moles of urea, right? So now, so how to do this? So the approach is the same. What we need to do
Excuse
is
me,
that,
doctor.
yes?
Now we answered the part A.
No, not yet. We didn't finish part A.
Okay.
So we're continuing with part A to find out what is the answer for part A. Now let's just calculate for carbon dioxide how much urea it can produce. So again, the approach is the same. What we need to do is
Yes.
here is to find out molar mass of carbon dioxide, right? So what is the molar mass of carbon dioxide? Can you tell me?
Molar mass of the carbon dioxide.
18.
No.
12.
No. Okay.
40.
44. Yeah, so it's a little strange that you have a problem to find out the molar mass because you last time you passed the quiz, right? And everybody passed, most of you passed it quite well. So I expect that you know these kind of things. So it's gonna be gram per mole. 44 or gram per mole. So now approach is the same. We have amount of carbon dioxide. So we need to divide this amount by molar mass of carbon dioxide. So this is going to be 44 here rather than 47. It's a mistake. So can you calculate what's going to be the answer for this?
Doctor,
Yeah.
it's equal.
Yeah.
Wait. 27.8.
27.8 moles.
Yeah.
Now, this is of carbon dioxide, right? This is carbon dioxide.
Carbon dioxide.
Yeah. So now let's look at the equation again. So we know that 1 mole of carbon dioxide produces 1 mole of urea, which means that 27.8 moles of carbon dioxide will produce 27.8 urea, right? Moles of urea, the same thing. So this is what is written basically here to multiply 1/1 because it's a ratio is 1 to 1. And then the answer it should be 27. It's wrong here, 27.8 moles of urea. Now I have a question. Can you think which of these two now is the limiting reagent in this process?
It's ammonia.
Yeah, why it's ammonia?
Because it give the height reacting, the limiting reacting of moles.
Of what?
Of moles.
Of what?
Of moles of urea.
So it gives. Say it again. What?
It gives the high limiting the reagent of urea.
Okay, so how much did it produce of urea, ammonia? You say ammonia is limiting, right?
Yeah, I know. Yes.
Yeah, so how much urea did it produce?
Oh, I'm sorry. That's what. I'm sorry, it's carbon dioxide.
Okay, so
Because
why?
it give 27.
Okay, so you say that carbon dioxide is limiting, right?
Yeah.
Okay, so why? Because it produces more urea, right?
Yeah.
Okay, so do you guys remember when I was talking about hamburgers and stuff like this? If you remember that story.
Yes.
Good.
Okay, so do you remember that we discussed about, okay, we lost one of the bread and we couldn't produce, say, we couldn't make 2 hamburgers, right? So we lost one of the
Right.
bread. And then we said that the limiting is bread in there, right? Because everything depends on the bread. So because of bread, we could make less amount of hamburgers, right?
Right.
Okay, if you think about that story and compare to this story, which one would be limiting here, ammonia or carbon dioxide? Okay, recall that story about hamburger. Imagine that you have
Yeah.
3 breads, but everything else you have for 2, like 2 cheese, 2 meat, everything 2. You could make 2 hamburgers if you had 4 breads, right? 4 piece of bread, but you have
Yeah.
only 3, and because of that you can make only 1 hamburger. So bread is limiting, right?
Right.
Okay, so what is the situation here? Which one is limiting?
Ammonia, Victor.
Okay, why it's limiting ammonia? Because we already discussed once that it was limiting, then we changed it to carbon dioxide, but now we need to find out which one is limiting. So why ammonia is limiting?
Maybe the gas of CO2 is completely accessible for all reactions, but ammoniac is not.
Okay, so our calculation shows which one is limiting. In this particular case, ammonia is limiting. Why it's limiting? Because we found that it produces less urea, so it can produce less urea. So it means that once we produce this amount of urea, the reaction will stop because we do not have more ammonia, right? So we used up ammonia completely. So the reaction will stop, okay? But unlike this, carbon dioxide can produce 27.8 moles of ammonia, which means that it can produce more than ammonia, right? So ammonia can produce less urea, carbon dioxide can produce more urea. So in this particular case, so it means that once we used up ammonia, the process will stop, right? It means that we produced only 24.9 moles of urea. But there is 3 more moles to produce by carbon dioxide, but it cannot do anything because ammonia is used, right? So in this case, ammonia is limiting. Do you guys understand or not?
Can you
Yeah,
repeat it?
exactly. Here,
Actually, don't understand 50-50.
Okay, so let's do it. Let's think about this one again. All right, so you have, say, this amount of ammonia, okay, and you have this amount of carbon dioxide. So they react, okay.
Okay.
So according this reaction, some kind of amount of urea is produced. Say we don't know how much, right? But once we reacted this one to, so this is ammonia. This is carbon dioxide. Okay, so ammonia reacted with, say, this amount of carbon dioxide. All right, so and then ammonia completely was used, completely. So after it reacted with particular amount of carbon dioxide, we produced 24.9 moles of urea. Okay, so but we have this amount of carbon dioxide left, right? Okay, this part was left. unused. It was left unused. Okay. So because of that, this was completely consumed, completely used. This was completely used, but only reacted with this amount of carbon dioxide. And this part was left unused, this one, which is like, or maybe if it is better for you, I can just do it like this way. Say this is used from carbon dioxide. Okay. And the rest is left, this white stuff is left, unused. So because of this situation that once the whole ammonia was consumed, the reaction cannot proceed. It cannot make more than this amount of urea. Okay. So this is why this reaction will stop. But you have left a little bit carbon dioxide, right? It just excess reagent, so it cannot do anything. We just stay unreacted with anything, okay? So how did we find this out? How did we find that ammonia was limiting? So it produces less urea. We calculated it that according this amount, it produces less urea, that amount which is given like carbon dioxide, okay? So carbon dioxide, if we increase amount of ammonia here, then we can use up the whole carbon dioxide, and maybe we can make this amount of urea, but we do not have that much ammonia, okay? So because of that, everything depends on how much ammonia we have. Again, once it's used, we can produce only this amount of urea and the reaction will stop. Because of this, ammonia is a limiting reagent. Is it clear or not?
Yes, it's clear now.
Okay. All right. So let's just, yeah, there was, oh, why did I discard it? Actually? Can you go back? No. Yeah. Anyway, it's recorded, so you can see this, all these notes you can see on in recording. So, but there is another question, right? There is another question. Calculate the mass of urea formed. How do you think? So this is 27 here, 27.8, right? So can you calculate the mass of urea formed if we take this amount of ammonia, this amount of carbon dioxide? How should we find the mass which is formed?
Doctor,
Yeah.
to find the mass of urea, we used the limiting reagent of ammonia.
Yes. Yeah. We need to use
the mole.
Yeah. So we need to use results from limiting reagent, which is ammonia in this case. So what was the result? Yeah.
Yeah, at 2040.93 mole.
Right. So this is
and we find the molar mass of urea.
right.
And calculate and finally we find the mass.
Exactly. So that's correct. So we find the molar mass of urea, and then we'll calculate the mass of urea. That's true. What about the question C? How much excess reagent in grams is left at the end of the reaction? So which is the excess reagent here?
Excess reagent.
Yeah. So one is limiting, the
Carbon
other
dioxide.
one. Yeah, carbon dioxide is excess reagent. Exactly. So
Why, doctor?
so because ammonia is limiting, so if one is limiting, the other one is excess.
Yeah. Okay.
So, so how much left this carbon dioxide in this case? How do you think? How many moles of carbon dioxide left unreacted? This is what we need to find first. Okay, so I
I
showed,
think
yeah, say it again.
I calculate that. I think it's 2 moles, 0.8778.
Yes, it's going to be 2.87 moles, right? So it's
Yeah.
number amount of carbon dioxide left unreacted. Exactly. How did you find it?
I increase the number of mole of carbon dioxide from ammonia. More
Okay,
ammonia.
so simply you subtracted,
decrease.
yeah, so you just subtracted this from here, right? So you just take this one,
Yes.
so it's 27.8 minus 24.93. This is how you found it. Okay, so this is 2.87 moles. And then you will find the mass. If you know the number of moles of carbon dioxide, you can find the mass of carbon dioxide. So this is how we answer all these A, B, C questions. Any other questions here?
For me, it's everything is good.
Okay, no more questions. Okay, so let's just continue with some more things here to finish, because we started talking about concentration, but we couldn't finish it. So last time I told you that concentration can be found as moles per liter, right? This is how it can be found, this concentration. So yeah, so if we know number of moles and we know the volume, of in which this number of moles of anything is, so we can find the concentration. Okay. If we don't know the volume, we never know the concentration. We just know the amount, but we don't know the concentration because it needs to be calculated per volume. You guys understand? Okay, so the equation for that, so usually concentration is called molarity. So, and this capital M corresponds to moles per liter. They're the same thing. If you see this capital M, it means that it's moles per liter. Okay. So you also can express concentration as weight volume percent, or volume percent, or parts per million, ppm. But we mostly will focus on molarity, which is moles per liter, and how you can find the molarity is written over here. So if you want to find molarity, you need to divide number of moles of solute on liters of solution. Okay, so this N is number of moles and V is the volume. All right. So now let's just see how can we use this information in reality. So let's just see the example. It says over here how many grams of potassium dichromate, so this is potassium dichromate, are required to prepare 125 milliliter solution whose concentration is 1.83 m. So which means that this is 1.83 moles per liter. Okay, so it means, in other words, simply saying it is 1.83 moles in 1 liter. Okay, but what is the amount of solution we want to prepare? What does it say here? How much solution we want to prepare?
125 milliliter.
Right, 125 milliliters. So 125 milliliters, if we express it in liters, how much is this one is in liters?
0.125 liter.
Right. So we need to prepare 0.125 liters, which gonna be X amount of moles, right? Because if we have 1.83 in 1 liter, so in this amount it's gonna be X, right? Can we calculate the X? What is X? Can somebody calculate it?
Doctor,
Yeah.
it's 0.229.
Right, 0.229 moles of potassium dichromate, right? So we found amount of potassium dichromate. This is in moles. So this should be taken in moles to make solution which is 125 milliliter, right? But we should measure it on balances, right? So we need to measure somehow this amount of dichromate. So how can we measure it? So on balances, we need to measure it in grams because balances gives you the amount in grams, right? Yeah.
Can you repeat what you say because my internet is lagging?
Yeah. So we found the amount of potassium dichromate. This is potassium dichromate in moles. So the unit is moles here, right? So this is the amount of potassium dichromate in moles to prepare solution of 125 milliliter. Okay, but we need to prepare this solution physically, for example, right? So how can you prepare it? So we need to measure it on balances, take this amount on balances, and then prepare solution. So we cannot measure moles on balances, right? On balances, we need to measure grams. So it means that we need to convert this one in grams. How to do this?
Doctor, we have right now more, and we can find the molarity of potassium dichromate.
This is okay. So we know the molarity.
Not molarity, molar mass.
Yeah, exactly. We need
molar
to find.
mass, I'm sorry.
Yeah, we need to
Because
find
one mole of potassium dichromate equal molar mass of potassium.
Exactly, it equals to molar mass of potassium dichromate. So this is already calculated here. So this is the molar mass of potassium dichromate. So basically what we need to do is that we need to, I mean, this is the same thing if you do like this way. This is 0.229 moles divided by 294.2 gram per mole. I'm sorry, not divided, I'm sorry. We should not divide, we need to multiply. Okay, so what is basically written here?
We delete mole.
So we need to multiply number of moles of dichromate with molar mass of potassium dichromate, exactly. So and then we'll find that it's 67.4 grams of potassium dichromate. So this is how we find the mass of potassium dichromate, which we need to prepare a solution of 125 milliliter, which has the concentration or molarity of 1.83 moles per liter. Okay, now I want you to read this one here and think, and then we'll discuss how to make how to solve this problem. Think about this one couple of minutes. Oh, there is only 2 minutes left, but let's just read this one, and once the Zoom is off, we come back and solve this problem.
Okay. Doctor?
Yes.
Doctor, we have already the mass of glucose.
So okay, so you need the mass of
To add
glucose.
it, glucose gram 4.07 grams of glucose, and we have to find the molar mass of glucose.
Right.